Hello everyone, I am Provakar and I will present the paper Automated Whitebox Fuzz Testings. The authors are Patrice Gottfried, Michel Y. Levin and David Molnar, and this paper is a collaboration of Microsoft and UC Berkeley. My presentation has 6 contents. First, I will say about something background. Then I will talk about what is the problem motivation of this paper. Third, I will say about what the solution the authors have proposed. Then I will talk about the evaluation results. I will talk then the advantage and bad sides of these papers. I mean limitations of the papers, and finally I will talk about the conclusions. So first, let me talk about fuzz testings. What is fuzz testings? Fuzz testing is an effective technique to find security vulnerabilities in software applications. Nowadays, both developers and testers actually apply random mutations to well-formed inputs. Then they test the resulting values to see if there is any error occurring. So in fuzz testings, good inputs are mutated to some different formats so that it can help to detect security vulnerability in software applications. Fuzzer has 3 key components. The first component is POET. It creates the malformed inputs or test cases. Second component is the courier. It delivers test cases or inputs to the target software. And the third component is the oracle. It detects if any failure has been occurred in the target software applications. Nowadays, fuzz testing is very popular because, I mean, in well-known inputs, it's difficult to find bugs, and it is not possible always to check if there is any hidden bugs in the software applications. But by fuzz testings, it's become easier to detect the security vulnerabilities or any kind of bugs in the software applications. And nowadays, fuzz testing is very popular, and lots of fuzz tools are available like Synopsys, Pstech, Google, OSS Fuzz, etc. Now I will talk about what is the motivation behind this paper. First, I will say about systemic dynamic test generation that is very popular in nowadays fuzz testings. This test generation technology, a form of dynamic program analysis, is created that attempts to compute test inputs so that it can be used to drive a program along a specific program path. However, with the existing dynamic text generation, there are some problems mentioned in this paper. The first problem that is mentioned is that the number of executions path in the program under test is very huge. And if the application is very large, then it's become actually very large. Second problem is mentioned that symbolic execution, constant generation, and constant solving are imprecise for large applications. Actually, these are tasks of dynamic text generation. So we are saying that dynamic text generation is not effective for large application actually with the existing approach. To address this problem mentioned in the previous slides, in this paper, the authors have proposed an alternative technology of whitebox fuzz testings. The proposed approach can record a run-of program under test with well-formed inputs. Then it symbolically evaluates the recorded trace. Third, it collects constraints on inputs according to the program uses by the developers. In fourth step, it uses constraint solver to produce new inputs on the collected constraints. So these are the 4 steps followed, and in the final steps, it produces new inputs that help to do fast testings so that the developers can find out any bug is associated with the software applications. The algorithm proposed in this paper is implemented on SAGE, which stands for Scalable Automated Guided Executions. To explain Whitebox fuzzing algorithm, let me first talk about these simple functions. So we see a function stop. So this program actually takes 4 bytes as input and contains an error when the value of the variable cnt is greater than or equal to 3. Now, if we run the program with random values for the 4 input bytes, then we are very unlikely to discover the error. And the authors have mentioned in this paper that by trying with random value, the probability to hit the error is very low. So actually with standing approach, if we try to find wrong inputs or if we want to hit the error, then the probability is very low. Okay, now let me explain what is the approach taken by Whitebox dynamic test generation. Assume we start running on the function top with the initial 4 letters string G double O D. So the leftmost path here, it represents the first run of the program on input good and corresponds to the program path P, including all 4 else branches of all conditional if statements in the program. The leaf path for that path is labeled with 0 to denote the value of the variable CNT at the end of the run. Now assume that we are running the program top with this new input G double O then exclamatory sign, which is denoted by label on. By repeating this process, the set of all 16 possible executions path of this program can be exercised. So from this tree, we can see that if this systematic search is performed in depth first order, these 16 executions are explored from left to right on this figure, and the error is then reached for the first time with CNT equal 3 during the 8th run. And full block coverage is achieved after the 9th run. So with existing approach, the possibility to hit the error is very low, but with this tree structure, we can see that if Whitebox dynamic text generation is used, then within 16th run, it is possible to hit the error. Okay, now I will talk about the SAG system architecture. So this proposed system SAG, it performs a generation search by repeating 4 tasks. The first task is the tester. It implements the required search functions by executing a program under test on a test input. The second task is the tracer. It runs the target program on the same input file again. The coverage collector replaces the recorded execution to compute which basic blocks are executed during the run. And the fourth task, the symbolic executor, it implements the expand function by replaying the recorded executions once again. And these 4 tasks are repeated. I mean, actually, they are run again and again with this order. Okay, now this section is evaluation. The proposed approach is evaluated, and this table actually shows statistics from 10-hour searches on 7 test application is seeded with a well-formed input file. From this table, I mean from the leftmost column, we can see the 7 applications. These are ANI, Media On, Media 2, Media 3, Media 4, Compress File, and finally Office App. This column shows the number of symbolic executed tasks during the search. Then the next column shows the total time spent in all symbolic executed tasks in second. The next column shows us the number of constants generated from the seed file. From the column test, we can see that the total number of test cases generated. From the column mean depth, we can see the mean depth per test case in number of constraints. This column actually shows us the mean number of instructions executed after reading the input file. And the last column shows us the mean size of the symbolic input in bytes. So we can see that lots of inputs can be generated using the proposed approach in this file. Okay, so here the left most table shows that SEC found 12 distinct stack hashes from 357 media on crashing files. So these are the 12 distinct hash, and the right table shows us 7 distinct stack hashes from 88 media to crashing files. From the evaluations, the authors have noted some observations. The first observation is that symbolic execution is slow actually. They have seen that total amount of time spent performing symbolic execution during each search is very high, and a single symbolic execution task is many times slower than testing or tracing a program. Another observation is that different files find different bugs. This is true because different file can contain different number of source codes, different numbers of functions, different types of functions. Another observation is that divergence are common. Actually, basics test setup did not measure divergence. So to do that, the authors then ran several instrumented test cases to measure the divergence rate. And another thing they found that bugs found are deep. So actually they found a lot of bugs using their approach and during the evaluations period. Now I'll talk about what the contribution of the paper is and what the limitations I didn't like about this paper. This paper introduced a new search algorithm for dynamic text generation. The authors have applied SEC to find bugs in different productions. They evaluated on two media parsing applications and they found some unique bugs within a small number of generations. So actually, with existing fast testing, developers required to generate to run the fast test many times to find the bugs, but with the proposed approach, it became possible to find bugs with a small number of iterations. Okay, now the limitations I did some things I didn't like about this paper, like the search method is not fast. If the application is very larger, then the search method becomes very slow. And experiments depend on operating system. Actually, the experiments taken place in this paper all are for Windows based applications. One reason I guess because this paper, the two collaborators of these papers are from Microsoft, so maybe that's why they focused on Windows-based applications. I don't know, but I think this is a limitation. They could focus on some other operating system-based application also. And from this paper, I found that they assumed some rules to design the algorithm. Okay, however, there are some limitations, but I still like this paper because in this paper they approached new approach of fast testings, and in the evaluation they have shown that their proposed proposed solution can gain good performance and with existing applications. And actually, in this paper, the authors have clearly explained what the problems are with existing solutions and how their proposed solution is better with some of the existing approaches. So overall, I like this paper. Now, to conclude my presentation, I would like to ask two questions to you. First, why alternative fast testing approach? So if you want to answer, you can email me the answers to me, or uh, but I will provide my answers for this question. So why alternative fast testing approach? Because existing path exploration is not good performanceable and not scalable for large applications. And with existing solutions, simple executions become imprecise due to complex program. So these are the reasons for why the authors proposed alternative fast testing approach. Although there are several existing fast testing approach, but they have the same problem, and to address this problem, I mean, they are not scalable, and path explosion is not good performance when the application is very large. So that's why the authors propose new approach. The second question I would like to present, why the proposed algorithm is heuristic based. My answer is that heuristic algorithm actually help to maximize code coverage as quickly as possible with the goal of finding bugs faster. So this is the reasons why the authors took the heuristic approach in their work. That's all for my presentation. Thank you very much. And if you have any questions, you can ask. Thank you very much.